Hey, and welcome back. Now we're going to be working on text problem 10-93 in the textbook. Go ahead and open up your textbooks to 1093, and we'll get started. Okay, now that you've opened up your textbooks, go ahead and read through the problem. Okay, now that you've read the problem, we can look at different indicators in this problem and determine what kind of physics we're going to use. So in the read step of this problem, we really want to look for those key indicators. We've got a block that's going down a ramp, and we have a pulley that's rotating, and it gives us the mass and radius of that pulley. Because we have a block going down a ramp, we're going to be doing a Newton's second law problem. And because we have a pulley that's rotating, we're doing a Newton's second law for rotation problem with the pulley. Our task for this problem is to calculate the acceleration of our block going down the ramp. For the physics of this problem, let's just go through the list. For Newton's second law on the block, we have to calculate the net force on the object and set it equal to the mass times the acceleration of the block. For Newton's second law on the pulley, we have to calculate the net torque and set it equal to the inertia times the angular acceleration. Some supporting equations we're going to need are the equation for torque, since we need it for Newton's second law for rotation, the link equation between the acceleration of the block and the acceleration of the pulley given our radius. Because it tells us it's a disk, we need the inertia equation for a disk, and there's friction on the ramp, which means we're going to need the equation for friction. In our draw step, we have our block, which is going down the ramp, and there's some friction on the ramp. It gives us the angle, and we have a pulley that's sitting up at the top of our ramp. We want to make sure in the draw step that we have a linked coordinate axis. What that means is when the block is going down the ramp, the pulley is going to be rotating in a direction. We want to make sure the direction of rotation and the motion of the block are both positive, or at least both in the same direction. For our givens in this problem, we're given the mass of both objects, the angle of the ramp, the radius of our pulley, and the coefficient of friction between the block and the ramp. And in order for this problem to work, we have to assume that there's no slippage on our pulley, which means that the rope is in constant contact with the pulley as it's rotating. For our solve step, because this is a Newton's second law problem, we have to go through Newton's second law analysis, which starts with free body diagrams. So first, let's go through the block as a little review. Now we isolate the block as it's going down the ramp. After we've isolated the body, we draw and label all external forces that are acting on the body. In this case, we have our weight force, our normal force of the ramp pushing back up. We have the tension of the rope pulling the block back up the ramp. And because the block is moving down the ramp, the friction force is opposite the direction of motion, and it's moving, so it's kinetic friction. After we've drawn and labeled all the external forces, we need to make sure that we have a coordinate axis, which we've identified in our draw step, and making sure that that's linked with our other coordinate axis, and a positive direction of rotation. Last, we need to label the critical angles and dimensions on our block, which our critical angle for this one is the angle between the weight force and the perpendicular to the surface, and the spot perpendicular to the surface, because that is not in line with our coordinate axis. Now we can start to do some Newton's second law analysis. Let's start in the y direction. In the y direction, we need to sum all the forces in the y direction and set it equal to the mass times the acceleration in the y direction. Our two forces in the y direction are the normal force, which is in the same direction as the y-axis, so it's positive, and a component of the weight force, which is opposite the direction of the y-axis, so it's negative. Because the block is not taking off in outer space or going through the ramp, it's not accelerating in our chosen y direction. Therefore, the mass times acceleration in the y direction is 0, which means that the normal force is our component of the weight force. When we sum the external forces in the x direction and set it equal to the mass times the acceleration in the x direction, we notice that there are three forces that are acting in the x direction. In the positive x direction, we have a component of the weight force, which is in the same direction as our x-axis, so it's positive. In the negative x direction, we have the tension force and the force due to friction. So our force due to friction, as we wrote down in the beginning, is the coefficient of friction times our normal force, which we solve for in the y direction. and our tension is going to be uniform throughout the rope. We can set that equal to the mass of our block, and only our block, times the translational acceleration of the block. We've already identified that the block is only accelerating in the x direction, which we've chosen in our coordinate axis. And since we're solving for the translational acceleration, we can go ahead and write that down. Let's move over to the pulley. So for the pulley, we have to go through the same steps in drawing our free body diagram. We isolate the pulley. Then we draw and label all external forces acting on the pulley. We still have the weight force. Gravity still exists when there's a pulley. We have the normal force. And we have a tension force, which is going down the ramp. Now just remember that all of these forces are vectors, so they do have a magnitude and a direction. Now, the next step in this is drawing and labeling our coordinate axis. We want to make sure that our coordinate axis is still linked to our original coordinate axis, and the direction of rotation is the same as the direction going down the ramp. So the positive direction of rotation indicates the block going down the ramp. Last, we have to label our critical angles and dimensions, which for this problem, our critical dimension is the radius of the pulley itself, and our critical angle is the angle between the radius of the pulley and the tension. So our position vector going from the axis of rotation to the point of the force and the tension. With that, we can conduct Newton's second law analysis and find the net torque on our object and set it equal to the inertia times the angular acceleration. The net torque on our object, well, we have to look at every force that is causing a torque. So a force that is acting away from the axis of rotation and is going in some direction that is not in line with our position vector going from the axis of rotation to the position of the force. Therefore, the only force that's causing a torque on our pulley is the tension force. And our torque, due to the tension, is the position vector for our radius, and it's crossed with the tension force. We can set that equal to the inertia of the pulley, which is modeled as a disk, so we can write that down from our original physics equations, and it's times the angular acceleration, which is the translational acceleration divided by the radius of the pulley. Now at this point, things start to cancel out, which is kind of nice. The radius of the pulley cancels out with the square, and once we solve for the magnitude of our cross product, it's the magnitude of the radius of our pulley times the magnitude of the tension times the sine of the angle between those two, which is 90 degrees. So that goes to 1. Additionally, the radius of our pulley is on both sides of the equation, so it will also cancel out, leaving us with just the tension on the left side and 1/2 times the mass of the pulley times the translational acceleration on the right side. At this point, we have an expression for the tension given to us by our Newton's second law analysis for the pulley. We have an expression for the normal force given to us by the y direction in Newton's second law analysis for the block. And we have an overall expression for the direction of motion of our block. So we can substitute the normal force and the tension force into our third equation and isolate the translational acceleration of the pulley, or of the block, excuse me. Now we have an algebraic expression for the translational acceleration of our block going down the ramp, and it's in terms of just our given variables. Make sure that when you have algebraic expressions, it is what you are solving for in terms of your given variables. After you substitute all the numbers in from text problem 1093 and evaluate, you'll find out it's about 3.56 meters per second squared, which since our least significant figure is 1 3 kilograms, 1 3, then it's one significant figure, which gives us 4 meters per second squared. Checking on it, we have the proper units since it's acceleration, we have the proper amount of significant figures, which we just discussed, and it seems like a reasonable answer for a physical situation. Thanks, physics fans. Have a great day.